In this episode, we are going to talk about the limit comparison test. Limit comparison test. In previous episode, we talked about the comparison test. So here we are going to find the limit of that test. Are we okay? So the rules in limit comparison test is quite different from the ones in comparison test. So please pay attention. So here we are going to consider two series. So for example, we consider a series AN as the first series. That series should be greater than what? 0. And we are also going to consider another series. So within a single series given, we are going to derive the AN and we are going to also find what? The BN. That BN should also be greater than 0. So with the rules of limit comparison test, it does not necessarily mean that we are going to assign the greater series to Bn and the smallest to An, just like what we did for comparison test. So in limit comparison test, we are going to assign each series to one of them. But the rule here is that whatever series we assign to An should be greater than what? 0. And the series we assign to Bn should be greater than 0. Now, if we are able to get the two of them, this is the rule. The limit comparison test is going to say that we should find the limit as n approaches infinity of the two series we have, which is An divided by Bn. This is what we are going to do. So with the limit comparison, if we are able to solve this expression and the answer that comes out is going to help us judge the nature of the series. So here we have L. Now, with limit comparison test, please pay attention. What we are going to see is that both series are going to converge or diverge. Note, after our solution, both series are going to converge or diverge. Alright, so for comparison test, we were not sure of some instances. For comparison test, we knew that if our Bn converge, then the smaller one An is going to what? Converge. But if the smaller one converge, we were not able to judge for the Bn. For that one, if you want to understand, go back to the comparison test episode. But unlike that for limit comparison, the value of the answer that comes out is going to tell us that since one of the series is diverging, the rest or the other one is going to what? Diverge. Or since the other one is converging, the answer is going to tell us this one is also what? Going to converge. Very good. So our L is going to be a finite number. So here our L is going to be a finite positive number. So a finite number that is what? Positive. If that is the case, then we can conclude that whatever the first series is behaving, the second series is also behaving that way. It is very simple, very, very simple. What we have to know is that whatever series we assign to An is greater than 0, shouldn't be negative. Whatever we assign to Bn should be greater than 0. Then we will use the expression limit of An divided by Bn. Then we will solve to get a value. Are we okay? So for example, let's solve this and see. So we are to solve summation from n is equal to 1 to infinity of 1 on root of n plus 1. We are going to determine if this series is going to diverge or converge using the limit comparison test. Are we okay? So straight away, I will assign my an to the series this. So you see, I'm not looking for the larger one or the smallest. I just assign the an to this series, the original one. Then my bn will be what I'm going to derive. It has some similarities with the comparison test. This one too, we are going to derive bn just like we were deriving the bn for the comparison test. So bn is also going to be derived from this. When n is large, plus 1 becomes what? Insignificant. So this is going to be 1 on root of n. This is the same as 1 on square root, which is n on the power half. So this is our bn. bn now is 1 on n raised to the power half. Now, can we judge if bn diverge or converge? Yeah, by the p-series test. By the p-series test, what happens to bn? Bn is going to what? Diverge, because the k is less than 1, right? Bn is going to diverge. But here, unlike the comparison test where we could have used this to judge the occurrence of an, right? Limit comparison does not give you the opportunity to make that declaration. You have to go through this approach. So yes, if we are to bring the idea of comparison test here, we can see bn is what? The largest. And if the largest is what? Diverging. Even with the comparison test, if the large one is diverging, we can't judge on the smaller one because the smaller one can diverge or converge. So you see that this is a scenario where comparison test cannot solve. The bn, which is the larger one, is diverging. So an can diverge or what? Converge. But limit comparison test will restrict the answer. Alright. So here what we are going to say is that since bn is diverging, let's find the limit of an divided by bn and see what we are going to get. So from limit as n approaches infinity of an on what? bn, what we are going to get is limit as n approaches infinity. Now what is our an? Our an is 1 on square root of n plus 1. Everything is dividing bn. And our bn is also now 1 on square root of n. So we are to solve this expression. Are we good? Alright, so let's look at how we are going to solve. Let's move to the next. So this is what we have. We have limit as n approaches infinity. What we wrote there is 1 on root of n plus 1. Everything divided by 1 on root of what? N. This is equal to limits as n approaches infinity of 1 on root of n plus 1. This can turn into multiplication, root of what? N on 1. This is what we have. Are we good? So this is the same as limit as n approaches infinity of root of n on root of n plus 1. Are we good? Alright. Now, if you learn your limit from calculus, we also have episodes of calculus here. You can go and check it out. Finding the limit here, what we can do is that we can divide both any or each of the expression by what? Root of n. So this is going to be limit, before we put in the value of what n approaches infinity, I can say root of n on the numerator divided by root of n, everything on root of n divided by root of n plus 1 on root of n. This is what we have, right? So this is going to give us limits. So this is going to be 1 on 1 plus 1 on root of n. This is what we have. Now, if we are going to put in the value of n as infinity, we can see that 1 divided by root of infinity is going to be, root of infinity is going to be a large number. 1 divided by that large number, this is approaching what? 0. So at the end of the day, what we are getting is 1 on 1, which is going to be 1. And remember, we said that after using the rule an on bn, we are going to get a number which is L, a positive finite number. So here, since we are getting a positive finite number over here, what does it imply? It implies that whatever one of the series is behaving, the other one is what? Behaving the same way. Please let me clear this. If we solve and we get a positive finite number, how one of the series behave is the same way the other is behaving. Are we good? But if we solve and let's say we get infinity, it means the second series is not behaving the same way like the other. Take it that way. Okay, this is the best explanation you can get. That's when you find this one and you get the L to be a finite positive number, whatever judgment you got, just like we got the judgment for Bn, which was 1 over n raised to the power half. And by P series test, this one is what? Divergent, right? If we get a positive value, that means our an, which we don't know, is also going by the same rule or the same way this is behaving. It is also going to what? Diverge. But assuming we solve and we are getting infinity, while this one is divergent, it means this one is not diverging. We don't have an explanation to that, right? Yes. So we are expecting to have a positive value so that we can make the same judgment based on what the other one is behaving. So with this, where our Bn is diverging and we had 1, which is a positive finite value, therefore our series summation n is equal to 1 to infinity 1 on root of n plus 1, which was also the an, is also what? Going to diverge. Very good. So the series is divergent. Let's look at the second example. Now, let's use the limit comparison test to test whether this series n is equal to 1 to infinity this one is going to diverge or it is going to converge. Very simple. So here we still have to find our an and bn, but not in the order of which one is the largest or which one is the smallest. So I will assign the original expression as what? An. So which is 2n squared plus n on square root of 4n to the power 7 plus 3. Then I will say my bn. Here I can reduce it for large values of n. Then I can say, I can ignore this and pick the large one. Okay, here too I can ignore the constant what? 2, right? So that I can get n squared all on here root of n to the power 7. Is it understandable? Yes. I can further say my Bn is going to be n squared on, this is the same as n 7 on 2. And by indices, we can say this is the same as n 2 minus 7 on what? 2. This is going to be n minus 3 on 2. This is also equal to 1 on n 3 on 2. Therefore, our Bn, this was just by the way the law of indices, you can check them out. This is the same as 1 on n 3 on 2. How it goes. So this is now the Bn series. Now we can use the P-series test. So one thing you see that the P-series test is very important for comparison test, limit comparison test. So you have to get used to it, right? So here by the P-series test, is this a converging or diverging series? Our K is equal to what? 3 on 2, right? That means it's greater than 1. This is 1 point something, right? So that means the series what? Converge. That is Bn converge. So we have to now use the limit rule, which is says limit as n approaches infinity of an divided by bn. If we're able to get a finite value, then we can conclude that an is also going to what? Converge. So now let's see. We are going to use this rule. So this is limit as n approaches infinity. What is our an? The whole equation given, which is 2n squared plus n. You have to be careful with your steps. 4n to the power 7 plus 3 divided by our bn. Now our bn is what? 1 on n 3 on 2. So this is the same as we are going to say limit n approaches infinity, 2n squared plus n, the square root of 4n to the power 7 plus 3. This changes to times as n 3 on 2 over 1. So now we can multiply this through, right? Multiplication. So this is also the same as limits as n approaches infinity of, when you multiply this by that, what are we getting? We are going to get 2n, which is 7 on what? 2. Law of indices, when they are multiplying, you are going to what? Add, right? So you are going to add 7 on 2 plus, if it multiplies that is going to be n5 on 2. Everything is going to be divided by this multiplying one is going to be the same thing, 4n to the power 7 plus 3. Now we have this. What do we do? Just like finding limits, we have to divide each term by what? A particular expression, so that we can cancel some of them out. So here you have to look through and look at what you are going to divide through. So here I would like to divide through by, check the numerator, I would like to divide through by n 7 on 2. And I would also like to divide this by square root of n on 7. Remember, this is the same as 1. This whole thing is the same as 1. Dividing by 1 is what? The same number. Right, you have to understand. N square root of n7 is the same as n7 on 2. So now, this is what we are going to do. Limits as n approaches infinity of, now the numerator, this is going to be 2n7 on 2 divided by n7 on 2 plus n5 on 2 divided by n7 on 2. Now let's come to the denominator. This is going to be root of 4 and 7. Please come here. When we have a root of a divided by root of b, this is the same as the square root of a on what? On b. Is that it? Yes. So if this whole square root is divided by this whole square root, then they can all come under one square root and divide by what? N7. Please do you understand? Plus 3 on N7. This is what we have. Now this is the same as limits as n approaches infinity. The mathematics approach, you have to pay attention and get it. So here, this will cancel out this, giving us 2. Are we good? By indices, when you subtract 5 on 2 minus 7 on 2, we are going to have plus n minus 1, right? We are going to have n minus 1, which is the same as 1 on n. Everything on the square root of, now this will cancel this, giving us 4 plus 3 on n raised to the power 7. This way. Are we good? So now let's move to this next page and simplify things. Are we good? Now this is what we have. We have limits as n approaches infinity of 2 plus 1 on n. You can use your calculator to verify things, okay? Root of 4 plus 3 on n raised to the power 7. This is what we have. So here we are going to now put in the value of n to be infinity. So if 1 is divided by infinity, it will approach 0. If 3 is divided by infinity raised to the power 7, it will also approach 0. So at the end of the day, we are going to have 2 on square root of what? 4. Now square root of 4 is the same as 2 on what? 2. Now 2 on 2 is the same as 1. So have you seen that now our using the rule limits as n approaches infinity of an on bn, we are getting 1, a finite positive value. Therefore, we can conclude that since our bn, which was this series 1 on n, 3 on 2, converge, and we are getting this positive finite value by the comparison test. This is limit comparison. By the limit comparison test, then our an, which is summation of n is equal to 1 to infinity 2n squared plus n square root of 4 and 7 plus 3 is going to what? Converge. So assuming we had infinity here, that means it is not a positive finite value. We don't know, so we can't say an was going to converge, but if we are getting a positive finite value, then we can conclude that the other series is also behaving the same way as the other is behaving. Are we good? All right, so this is 2 examples under the limit comparison test. In the next episode, we are going to solve a lot of problems. We're going to solve 4 examples on the limit comparison test. So maybe that place you'll get more examples and you get time to understand. Please pause the video at times and check out the calculations. Like the video, subscribe, and see you in the next episode. Thank you.